Hello students, today we will discuss about the behavior of light through petrological microscope. How the light passes through the petrological microscope from the mirror through the mineral up to the eyepiece, and what happens to the light rays when it passes through this path. So that is to be discussed through this behavior of light through petrological microscope. So let us discuss. The petrological microscope is used to identify rocks and minerals in thin sections. So to study these minerals, rocks, we allow the light to pass through them, or light is being transmitted through them. The variation in the rate of transmission of the light in the mineral sections or rock sections help to deduce optical properties by virtue of which the minerals are identified. So, what happens to the light rays, how they vibrate, whether they are easily allowed to vibrate or not, whether they pass with equal velocity in all directions or their velocity is found to be affected, found to be high or low. So all those features and the color characteristics of the minerals are being studied through the study of the behavior of the light through the microscope. So the behavior of light from the light source to the eyepiece through the mineral placed on the stage of the microscope is described in following paragraphs. Now we'll see what happens to the light rays. So this is the light source. It may be the plane mirror, as we see in case of simple microscopes, the plane mirror which allows the light to be reflected up into the microscope. Or we have the rheostat controlled light source, or electrical controlled light source that allows white light to pass through the polarizer, from polarizer to the condenser, from condenser to minerals, then through objective, analyzer, button lens, eyepiece to reach our eye. So in this manner the light moves. So first the source of light, and this from the light source the light is being allowed to come up, to enter into the polarizer. So this light is ordinary light. The light which comes from the light source is ordinary light. It is not polarized. And for optical study of rocks and minerals, it is required that light should be polarized. Therefore, we take use of polarizer or nickel prism. Generally in microscopes we take use of the nickel prisms. Nickel prisms are a type of polarizer. Let us say this is nickel prism and this is the polarizer, and it has the property to allow the light to vibrate in along north-south of microscope, and in this condition it goes up. So This is north-south direction and goes up. So light here it has been plane polarized. When you talk about polarized light in that case, light rays are found to vibrate in one plane and move in a perpendicular direction. If they will vibrate like this, they will move like this. So these are the polarized lights. So light vibrating parallel to north-south of the microscope pass through the polarizer and come up. So after passing through the polarizer, light has been polarized, and now they generally pass through the orthoscopic arrangement or conoscopic arrangement. Generally we allow it through orthoscopic arrangement, through the condenser, and when the light comes up, it enters into the mineral placed on the stage. There it gets doubly refracted when the mineral on the stage is belonging to non-cubic system, or remains as a single ray if it is a mineral which belongs to cubic system. So generally there occurs double refraction. From a single ray we get two refracted rays through the process of double refraction. So this is the two refracted rays. One goes with a higher speed, the other goes with a low speed. So these are the two vibration directions of the two rays, refracted rays. And these two refracted rays, they come up. One is the fast ray, the other is slow ray. If it is slow ray, this is the fast ray. So these two rays, they vibrate into mutual perpendicular planes and move up. So here the two rays are leaving the stage of the mineral, and now they are entering into the analyzer, which is called as the upper nickel. This is the upper nickel. It is upper nickel, or it is called as the analyzer. This is lower nickel or polarizer. As the name implies, this upper nickel analyzes the light that enters into it. We have two rays, one ordinary, the other extraordinary, both entering into the nickel. Each of them get doubly refracted. So let us say this is fast, this is slow. So fast ray on entering into the analyzer, it splits up into two components, O1 component, E ray component. The slow ray on entering into the analyzer, it splits up into O2 and E2. But the very function of the polarizer is that it will eliminate the O ray parts by total internal reflection. So only E1 and E2, which do not match with their velocity, one of them will be fast because one of them has been derived from the fast ray, the other has been derived from a slow ray. So they cannot be same velocity, cannot be of same velocity. So these are the two rays which are produced in the plane of the analyzer. They move up vibrating in the plane of the analyzer, and their velocities are different, so they will interfere. They will interfere, and the result will be the interference of light. So one ray is moving like this, another ray is moving like this, so there will be a resultant wave out of the interference of two waves. So the resultant wave's color will be seen as the interference color. So this is the phenomenon that happens when we simply allow the light to pass through the light source through a polarizer to the mineral, then from mineral to the analyzer. Ultimately, two rays are produced, one fast ray, the other slow ray, and they interfere finally to produce interference color. This fact we will discuss in detail. In simple microscopes, generally daylight is used to study the optical characters of rocks and minerals. But in advanced microscopes, the electrical method is used to provide white light into the microscope. It may be through rheostat mechanism or through lenses. By filtering the light, white light is allowed into the microscope. So white light enters into the polarizer which is placed above the light source. Polarizer, or it is the nickel prism. The function of the polarizer is to produce polarized light, and this polarized light, it may vibrate parallel to north south or east west of the microscope. This facility varies from microscope to microscope. Here we will consider that the light that comes up from the polarizer is vibrating parallel to the north south of the microscope, and in this condition it is sent up. So ordinary ray component of this white light has been eliminated, and the E-ray components have been allowed to pass through the polarizer vibrating parallel to the north south of the microscope, and in this condition they come up to meet the mineral on the stage of the microscope. So here we will discuss what happens when the light enters into the stage of the microscope. On the stage we may keep minerals, we may keep mineral slides, or we may not keep mineral slides. So, or we keep minerals of different systems. So depend upon the type of mineral placed, the behavior of light will be different. Therefore, we need to study the following cases. We have produced polarized light that is vibrating part north south of the microscope, that has entered into the stage, and we will study these cases. What happens? Let us say nothing on the stage of the microscope, because it is generally seen that as the polarizer and analyzer, they may be having the facility to be rotated. So in many occasions they may not be available in mutually perpendicular conditions. So to test that, we need to keep nothing on the stage of the microscope and then see whether analyzer and polarizer, when they both are in use, whether their vibration directions are mutually perpendicular or not. If they are mutually perpendicular, the microscope is in perfect condition to be used for the study of optical properties of rocks and minerals. Therefore, first case is we have to see the light property by keeping nothing on the stage of the microscope. In this condition, light passes the stage with the vibration parallel to the north-south, because north-south vibration is coming from the polarizer. So nothing on the stage, it will simply pass with north-south vibration and it will reach the analyzer or the upper nickel, whose vibration direction is east to west, because analyzer narration, polarizer vibration, they are mutually perpendicular, and this condition is called the cross condition. So east to west, that is perpendicular to the vibration direction of the polarizer, this light is not allowed to pass through the analyzer. Darkness results. It is because analyzer will allow that light to pass through it which is vibrating parallel to it or oblique to it, but not perpendicular to it. Perpendicular vibrations will not be allowed. Oblique and parallel vibrations will be allowed to pass through. So this phenomenon is observed or verified by keeping nothing on the stage of the microscope. This is first stage. Before we go for identification of any mineral slide on the microscope. Then let us keep a amorphous substance such as glass slide on the stage. We know amorphous substances cannot alter the direction of vibration of light coming from the polarizer. Hence, the polarized light with north-south vibration simply passes through the glass slide without any deviation in its path. It will come up, it will hit the analyzer perpendicularly. Analyzer will not allow it to pass through. Darkness results. Let us say third type, a section of a mineral which is called perpendicular to optic axis, or it is a section of a mineral belonging to cubic system. In those cases, what happens? Here the section cut perpendicular to optic axis or the mineral belonging to cubic system, both present a uniform atomic structure. That's why when the polarized light enters into them, whether it is cubic mineral or a mineral section cut perpendicular to optic axis of a mineral, in that case there occurs no deviation of light path in the mineral section. It vibrates parallel to north south as it was vibrating when it was leaving the polarizer. It simply passes through the mineral, enters into the analyzer, hits the analyzer perpendicularly, and no light passes through. Darkness results. than any other section. So we discussed that there is nothing on the stage of the microscope, darkness results. We have kept a mineral below cubic system, darkness results. We have kept a mineral section cut perpendicular to optic axis of a mineral, in that case darkness results. Now any other section we have to take. So here there will be double refraction. Here light coming from the polarizer faces double refraction, and from a single incident ray two rays are being produced. Two rays are produced. One of them may be fast ray, other will be slow ray, or one of them will be ordinary, the other will be extraordinary. Ordinary extraordinary comes into picture when we talk about a mineral section that belongs to either tetragonal or hexagonal system. But fast ray and slow ray, general term which is used for biaxial minerals, that can be applied to uniaxial minerals. So two rays are produced by double refraction, and these two rays leave the mineral placed on the stage and enter into the analyzer. And there they go for interference. So before these two rays go for analyzer, what happens to them? Let us discuss. Let us say the mineral through which these two rays are passing, that is having a thickness m. The velocity of fast ray is v1 and that of the second slow ray is v2. So the time required to the fast ray to pass the thickness m will be m by v1, or it will be t1. Similarly for slow ray it will be t2, that will be equal to m by v2. So time difference will be t2 minus t1, that will be m by v2 minus m by v1, or m into 1 by v1, v2 minus 1 by v1, that will be m into n2 minus n1, which is the difference between the refractive indices of the two rays. This is otherwise called as birefringence. So thickness into birefringence, it gives the time difference. And this is actually the retardation. This time difference between two rays is called the relative retardation of two rays. It speaks about which ray is at how much distance ahead of the other. So this retardation is really controlling the character of color that will ultimately be produced in the analyzer. If we have taken monochromatic light of single wavelength, then the phase difference between the two waves will be retardation by wavelength. This will be m n2 minus n1 by lambda. This is the phase difference. P, or phase difference. Thus phase difference for two rays traversing a mineral section varies depend upon thickness of the mineral section, birefringence value, wavelength of the light used. The two rays having phase difference between them enter into the analyzer. Each of the two rays gets doubly refracted in analyzer, and only the extraordinary ray components from each ray, fast and slow ray, are allowed to pass through the analyzer, vibrating parallel to the short diagonal of the upper nickel or analyzer, and that is east to west direction. As the ordinary ray components are eliminated, and E ray components are being allowed to pass through. And these two E ray components, they, through their passage through the analyzer, they try to interfere. They cause interference, and the result is interference color. The result is interference of light. Let me elaborate this fact. There is double refraction when the polarized light comes from the polarizer and enters into the mineral section. Two rays are produced, one fast ray, other slow ray. Both go up to meet the analyzer. And analyzer is either a type of nickel prism or it may be a polaroid, but there each of these two rays, each of these two rays face double refraction. So from S there will be one O1 component and E1 component. From fast ray there will be O2 component and E2 component. But the O1 and O2 components are eliminated as per the construction of the nickel prism, and only E1 and E2 components, they are allowed to pass through the plane of the analyzer. One moves at a higher speed, the other moves with a lower speed. One becomes fast ray, the other becomes slow ray. So in this condition they interfere. The interference may be constructive, or the interference color may rise, or there may be destructive interference, destruction of the interference. So how interference helps, how interference cancel each other, let us discuss that. So in order to study the constructive interference or destructive interference based upon phase difference, first let us analyze by taking monochromatic light into account. We have taken a light of single wavelength, the monochromatic light, and let us talk about a case when the phase difference is n lambda, where n is an integer. It will be having value from 1, 2, 3 like this. So first phase difference we can talk about, let us say it is 1 wavelength. So let us say this is one color, this is this is the fast ray, and the second ray or the slow ray is moving like this, and both have a phase difference between them, lambda. So in this condition what happens? This ray is passes like this. This ray, when it is coming up, there it is vibrating up, this is vibrating down. Both will cancel each other. There will be darkness. This wave will become extinct at the point A. So this is a case of cancellation of each other. Two waves have phase difference 1 lambda and interfere with each other. At point A, both will cancel each other, there will be darkness. So for darkness condition, the phase difference must be n times the lambda. N will be having value 1, 2, 3 like this. Now let us say the phase difference is 2n plus 1 by 2, 2n plus 1 by 2 lambda, where n is an integer starting from 0, 1 like this. So first phase difference will be 1 by 2 lambda. Second, it may be 3 by 2 lambda, like this. Let us consider the two waves with phase difference lambda by 2. This is the color for first wave, and this is for the second wave. Here what happens? They have the path difference lambda by 2. What happens? These two rays, they pass. Here there will be the resultant wave. The intensity of resultant wave will be increased because these amplitudes of both the rays will be added up. A1 plus A2, the amplitude of first wave and the amplitude of second wave, they add up to form the new amplitude. This will be new amplitude and this will be the resultant wave. And this is a case of help or constructive interference. Light will not become extinct. So 2n plus 1 by 2 lambda phase difference is the case to help the light rays to produce color. N lambda case is the case to cancel each other and produce darkness. So this is the case when we talk about the monochromatic light. But when we go for the optical study of rocks and minerals, we do not use the monochromatic light. We use the white light. So what happens when white light is being used? Let us take a case of n lambda. So white light is a combination of 7 colors. Their waves interfere in following manner. Let us say the phase difference is n lambda. The 7 colors, I will draw the 7 colors. Let us say this is color 1. And n lambda difference. So this will become extinct here. First color 1, wave 1. This is color 1, wave 2. They cancel each other. Let us take another color. This is color 2, wave 1, color 2, wave 2. So they will cancel here. So this is the position when first color was becoming extinct. But in that case, this color is present there. This color is present there. But this color is becoming extinct at this position. So here, the place where first color is becoming extinct, the second color is present with this vibration. Similarly, if we take any other color, that will be like this. It will be like this. So third color will become extinct. here at that place where third color is extinct, other colors are present. Thus, you will not get a condition of total darkness. When one color is becoming extinct, its complementary colors are present there. That has been shown here in form of color 1, color 2, color 3. When one color is extinct, the other color is present there, and we will never get a condition of darkness. So when you use white light, we will not get complete darkness. When the phase difference is 2n plus 1 by 2 into lambda, here it is the case of help. So the color will not become extinct. But when the case is n lambda, in that case also, when some colors are becoming extinct, the other complementary colors are present there. So we will never get a condition of total darkness. So this is the fact, and this fact has been analyzed here, and thus we see that when we take use of white light, we get interference color in cross-nickel condition. When we keep a mineral, anisotropic mineral on the stage, which first causes double refraction, and because of the double refraction, the two rays are being produced, they finally interfere to produce interference color. And this interference color is found to show several orders. But this interference color is classified into several orders based upon lightness, based upon whether they are deep colors, dull colors, or light and bright colors. Generally, stronger colors are the first order colors, first and second order, and the higher order colors are fainter colors. Or first order colors are deep and dull colors, higher order colors are light and bright colors. And it has been seen that this interference color that is produced by white light, it is otherwise called as the Newton's scale of interference colors, and these colors are divided into these orders as they have been described here. In first order there is no blue, no green. We have grey, white, yellow, red. Then in second order blue, green are there, which are not there in first order. So blue, green, yellow, red, blue, green, yellow, red, third order. In higher order colors, we get higher order whites or higher order pinks, brownish pinks, pale greens, or creamy. It looks creamy, so creamy color is higher order. So these are because the higher order colors, they mix up and it becomes difficult to separate. They become bright, and to identify these orders, we take use of the quartz gauge between cross nickels to identify what are the colors of first order, what are the colors of second order. We may use quartz gauge above the objective and see what are the colors of first order, because each order is found to end with a red band. So first order red, then second order red, then third order red. So as the wedge is gradually pushed into the microscope, the thin end will give the first order red, then thicker second order red. Gradually the colors they appear. So we can know about the different types of colors that come up through interference of white light. So we can be acquainted with the different colors that are seen in different orders. And in order to identify the order, we can take use of the quartz wedge. If we take monochromatic light, quartz wedge, at 1 wavelength, 2 wavelength, 3 wavelengths, we will get the dark band. This is darkness because n lambda, 1 lambda, 2 lambda, 3 lambda case, so there will be darkness. If we take use of the white light, then this will be ending with a red band, this will be ending with a red band. Grey, white, yellow, red, blue, green, yellow, red, blue, green, yellow, red. In this manner the colors will be seen. If we use white light and insert this quartz wedge to see the color. Grey, white, yellow, red at thin end of the quartz wedge. This will be first order. Blue, green, yellow, red, the second order. As the thickness increases in quartz wedge. In the higher order colors are white or washed out colors or creamy white colors. They occur towards the thicker end of the quartz wedge. And in order to know the birefringence value, in order to know the retardation value, we can utilize the Michael-Levy chart. After noting down the order of the interference color and the color present in the order. If we know the color and order of interference color, if we know the thickness of the mineral section, then by using the Michael-Levy chart, we can find out the retardation, we can find out the birefringence value. Generally, first order red has a retardation 550 nanometer, second order red has a retardation 1100 nanometer, third order red has about 1650 nanometer of retardation. By knowing the order of interference color and the color of type, it is possible to find out the birefringence and retardation value. So in this manner we use the Michael-Levy chart and determine the birefringence value and the retardation value. So this is all about what I wanted to discuss about the behavior of light through petrological microscope. Thank you all.